All right, starting the recording officially, and the screen share. Not going to forget. Going to win on that. I have a streak going of not forgetting the screen share. Don't want to break my streak. So just a couple updates in terms of things I've posted or announced in class or via email. I have Thursday, everybody is on Zoom, and this room is being taken over by comprehensive exams. So if you usually come in here to Zoom from, you'll need to find another place in the building or elsewhere. Let's see, I sent out an email this morning, but in case you haven't checked email, there is a link to a Word document that I'm going to be editing. I thought in case you wanted to play along and edit with me that it might be helpful to send you out the template. If not, I'm going to post the finished version afterwards, and so you don't have to worry about typing or writing as fast as you can. Let's see, another thing that is ready for those of you who are doing individual data analyses for your homework 4. You should have received feedback from me with respect to the plan of what you intend to do. If you didn't, it's because I sent you a separate email asking you specific questions, and once we agree on your plan and you answer my questions, then you can have your 2 points. And the rubric that I made for the assignment is posted on the due date, which is November 13th. That way you can see exactly what I'm looking for. If you have questions about your specific analyses and what would make sense, if you want to talk through strategy, I'm happy to do so over email or individual meetings, office hours, you take your pick. It's not supposed to be like you figure out absolutely everything on your own, but hopefully applying the principles and the things that we've talked about, this is your chance to show that you can extend it to data that you care about and hopefully get the start of something that could become a conference presentation, a manuscript, maybe even a dissertation, who knows. So some of you have some ambitious stuff planned, so I'm excited for that, right? Yes. Okay, move the thing here, there we go. All right, I think that's all the updates. Anything I'm forgetting or that you want to ask about, logistics-wise? So today we're talking about formative assessment number 4. The next thing you have on tap is homework 3. I've heard that it is a lot, but also fun. So take that for what it's worth. Your fellow classmates have weighed in on that. Let's see here. So it took me a few tries to get your formative assessment set up in the format that I wanted, where you had multiple drop-down menus. And in so doing, I had to fuss with the due date and whether you could see it and whether you could not see it. And where I ended up landing, apparently, is that you could see your scores immediately. So I noticed that several of you made 4 or 5 attempts to try and get everything right, which I thought was kind of funny. I promise you get 2 points no matter what. So I have not updated the scores in Icon because I didn't want to mess with it and make it so you couldn't see what you had missed. But I have updated your scores inside my spreadsheet that I keep that uploads to the online homework portal. And after class, I will go through and get your 2 points. So it's still the same effort, but more important than getting the right answer is understanding why the answer is right. So that's what I wanted to make sure that we went over as a group. And so I have this little table built that gives the starting model and then has what should happen to each variance component in the model as we add additional fixed effects of various kinds. So, we ready to look at this? Maybe? Nod? Yeah, not rhetorical? Does that work? Zoomers, you with me? Can you hear me and see me? No, we're dancing. This is like a thumb dance thing. Okay, we can dance. That's fine. All right, so here's my starting model. I'm using somewhat generic notation, but it's following the usual way that I label things. So within cluster X1 is cluster mean centered person variable. Cluster mean X1 is the cluster mean of that variable to be used at level 2. And the within cluster variable has both a fixed slope and a random slope. The cluster mean has a fixed slope only. There's also a random intercept in the model. So in terms of which types of variability could be explained by which fixed effects, as we add them, there's 3 choices here. We have the level 1 residual variance. That's the variance of the e's across people and clusters. We have the level 2 random intercept variance, which is this guy right here, U0, the variance of the U0s across clusters. And then the level 2 random slope variance across clusters, which corresponds to this guy. So it's this variable specifically, need to add a 1 there, because there's going to be a 2 showing up that we are looking at. Can I make that bigger? There we go. Okay, with me so far? All right. So here's my starting model, and I had recommended that it might help to actually rewrite the equation and adding things as we add, so I'm going to do that with you. So we'll start here and add stuff as we go down the page. So the first one was adding a fixed slope for a new level 1 predictor that was also cluster mean centered. So what do I need to change my equation to be able to add this term? Where does it go? Level 1. So I'm going to copy here inside my equation. And what number should I put here? What comes after 1 if you're counting? 2. All right. See, I promise, nothing but softballs. There we go. And then this is going to, the E is moved over. Come back. There we go. Do I need to do anything else? I think I do. I do. As many beta placeholders as you have at level 1 is as many level 2 equations that you need, one for each. So I'm going to do this, copy that. Oh, that's a typo. That's a 1. I can never see my typos until I'm sitting in front of you, and then they are apparently clear. So forgive me for being imperfect. It happens. Okay, is this right, or do I need to keep typing or remove things? I'm adding a fixed slope. Do I have one of those? Not meant to be a hard question. I swear, I'm not tricking you. Go with your instincts. Do I have a fixed slope in here for my new predictor? Yeah, yes, I do. Yes, but I didn't say add a random slope, so I don't have one of these yet. And indeed, I don't in this story problem on purpose. So the fixed slope that I've added is gamma 2O, which goes into my placeholder, which eventually multiplies the level 1 predictor. Okay. So then now the question, what happens to my variance components? First question, see if I can get this back on the screen. Maybe. There we go. Level 1 residual variance. 3 choices. Up, down, same. What are we picking? This can be a finger question or a Zoom icon question. You take your pick. Level 1 residual variance. After adding this new term right here. I'll highlight it to make it more obvious. We got 1 vote for up, 2 votes for down, 3, 4, 5 votes for down. Anyone else want to vote? Okay. What's the rule?
Down.
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 That was an enthusiastic down. That was not vague at all. The downs have it. You explain a level, if you add a level 1 predictor, which is a person characteristic, it should explain person variance, which is level 1 residual variance. Why is it that some people from the same cluster are higher or lower? Part of the reason, if the slope is significant, should be this variable right here. And by significant, I mean like a decent enough effect size that where you'd see something happen. That's sort of my shorthand for that. Now for the trickier ones. Let me do the slope variance. Let me go over here. What should happen to the slope variance for within cluster X1, which is this variance right here? Up, down, or stay the same? Should stay about the same. You didn't change anything with respect to that slope. It's still doing its own thing. Now this one. What happens to the intercept? We got 1 vote for down. This is a hard one. You thought it was the same? Okay. Anyone want to vote up? So here's how to think about this. This new variable right here is cluster mean centered. That means it only contains within information. It can only possibly explain level 1 residual variance. Anytime that level 1 residual variance goes down, random intercept variance goes up to compensate. So the Zoomers say, I know the answer, but not why. It does go up. The answer is because the way that the random intercept variance is estimated is not just between cluster mean differences. It's between cluster mean differences as observed in the data, minus the part of that that is expected by chance just from who happens to be in that cluster. So we talked about this like 2 months ago or something. If I took this entire class and I assigned you guys into like 5 different groups, and you computed the mean height of the people in your group, are those means going to be exactly the same? Probably not. If it's truly random assignment, they should be close, but they're still going to wiggle a little bit. So that sort of wiggle a little bit based on chance is what the random intercept gets subtracted off to make the model estimate of it as the true between group variance, between cluster variance. So anytime that the residual variance goes down, the correction factor that is formed by residual variance divided by level 1 sample size then is reduced, and the net result is that the intercept variance goes up. So anytime residual variance goes down, because it's explained, intercept variance is going to go up at least a little bit to compensate. So that's a tricky one. But I want you to be aware that it happens. That way, if you see it in your data, you don't think you've done something wrong. The more the reduction in the residual variance from a level 1 fixed effect, the more the level 2 intercept will increase. Okay, any of that you want to hear again or hear explained differently?
I guess I still just don't understand why, I know you just explained why it goes up, but like in my head, I feel like it's a group, like it's a chunk of variance that was introduced, and a part of it is like the first part goes down because it's attributing to that, right? Like you now know that variance has to do with this variable. So I don't know how the leftover is put into another, like I still don't understand why it goes up.
Okay, fair enough. Let me open, let's see, where would this be? I think it is lecture 3. Let me see if I can find it. There's a particular equation I'm looking for.
Sorry.
Nope, don't be sorry. This is why we're doing this. Here it is.
Lecture 2.
Yeah, it's in lecture 2, but it's also in lecture 3. I just found it here. This is lecture 3, slide 37. Fixed slopes of level 1 person predictors that do not have level 2 variance, meaning you've cluster mean centered your level 1 predictor. That should reduce the residual variance, which will make the intercept variance increase. Because what the model is giving you is what it thinks is true, which is the observed between cluster mean differences minus this correction factor. So anytime this residual variance goes down, less is subtracted off, and the net result is that true goes up.
Okay, that kind of helps seeing that equation.
So you will see this much more if you have a very small cluster. So like in longitudinal data with 3 or 4 occasions, this happens like much more, this tendency is much more readily observable. In cluster data where you have a lot of people per cluster, because level 1n is so big, it sort of counteracts this and makes it not as much of a thing. But you will see an increase in random intercept variance if you get a sizable decrease in residual. And that's why even if your interclass correlation is 0 to start with, it may not stay that way. Because if you explain residual variance, the intercept variance is going to go back up. Your interclass correlation that's conditional is going to go back up as well.
Okay, thank you.
You're welcome. Other questions or comments? So I wouldn't count the increase in random intercept variance as like a real thing. Like it doesn't mean your model's misspecified. It's just a consequence of reducing the residual. All right, next one. Add a significant fixed slope for CMX2. Okay, I'm going to borrow my model here. Where does it go? The cluster mean of my new level 1 predictor. 2? Vote in 2? Which 2? I got 3 of them. Yeah, that stands for intercept, which I now have room to write out. And by the way, if you're going to write out equations for people, labeling them like this, they will like you better. Like, what is this predicting? Don't make me figure this out. This is predicting the intercept. This is predicting the first slope. This is predicting the second slope. So yes, that is correct. I'm going to go in here, grab that. And what subscripts do I give this one? It was O1 for here. This one should be what? O2. Yes, and it's O because we're predicting beta 0. It's 2 because this is the second predictor of beta 0. And I'm going to return this so that it looks a little bit better. There. And then this is 2. It can be centered at 5 or 6 or whatever. It doesn't really matter. Okay. Do I need to do anything else to my equation? Go over. There. No? Is that good? Yep, that is correct. This is sufficient. So now, what happens to my variance components? First column is level 1 residual. If I add a new level 2 predictor of the intercept as a main effect, what happens to my level 1 residual? Up, down, or stay the same? Got to vote for same? Another vote for same? Same? We're achieving consensus here in the classroom. Oh, consensus on the Zoom window, yes. Level 2 main effects predict the intercept. Ding, ding. What happens to my level 2 intercept variance if I add a significant level 2 fixed main effect? Votes for down in the room? Zoomers? Lots of votes for down, that is correct. Intercept variance goes down. Part of the reason why clusters had different means is now attributable to whatever this variable is. How about the random slope for within cluster X1 specifically? Okay, same, up or down? Got 2 votes for same, 3 votes for same. Zoomers, 1 vote for same, 2 votes, 3. Same is correct. We haven't done anything with respect to this slope. So this U1 should stay about the same. About the same being the operative phrase. It'll wiggle, but about the same.
Could we unhighlight the within clusters and then highlight the new cluster mean?
That is a fantastic idea. Correct. Nope, nope, come on. Sometimes it lets me repeat things and sometimes it doesn't. So yes, we are at this step right here. That is the new thing. Not the U, that was there before. No, really. Take that. Nah, I win. And by the way, the folks who are working on individual data analyses, one of the things I'd like you to take a try at is writing your final model equation. So this is hopefully giving you some practice at working through this as well. And it doesn't have to be right, but you do got to give it a try so that I can help you get it right if need be. Revisions on both assignments will be due at the end of finals week. Okay, any questions on that one? Gesundheit. Next up, fixed slope for this. I have CMX2 times WCX1. In other words, a level 2 predictor interacting with a level 1 predictor that was cluster mean centered. So what do I call this? What kind of interaction? It has a special name. Cross level. Where does it go? Does it go in my level 2 model or my level 1 model? Got to vote for 2? Which one? Zoom this in so we can see it a little bit better for a second. We got 1 vote for this equation. Anyone else want to vote? Okay, no one wants to vote. Yeah, we got, you say intercept as well? Also go into intercept zoomer question. The answer is it only goes right here. So we have gamma, what is it going to be? What's the subscript on this? 1, 1, correct. Why is it 1, 1? Because it's predicting beta 1.
And it's the first, like, 1 is after 0.
Yes, and because 1 is after 0, that is correct. It is the first predictor of the level 1 slope here. So I need Cm, what do I call this, x2. This gets a C because it's a cluster characteristic. So when all is said and done, all of these things are packed into beta 1, and it comes back up to level 1 to multiply this. That's how it becomes an interaction term. It does not need to go into the intercept because it's already here. So the same rules about interactions and main effects still apply. Before you add an interaction term, you would want to make sure the main effects of both variables are already included. That way the interaction does what it's supposed to do. And let's throw a centering on here. If I centered it at 7 instead, does that change anything? It would only change the fixed intercept, and it would change the interpretation of the main effect of within cluster x1, because this is conditional on whatever 0 means over here. So it doesn't matter which constant it is, other than that, changing the interpretation. Okay, now we need to unyellow that and re-yellow that. There, now it let me do it. Excellent. Okay, questions on that? Now, residual variance. Up, down, or same? 2 votes for same, 3 votes for same. Some people do not want to vote. That's okay. Zoomers? Residual variance in this model, up, down, or same after adding a cross-level interaction. 2 more votes for same. Yeah, it should stay the same. What about random intercept variance? Another vote for same? Same. Got to vote for down on that one. Anyone else want to vote? This one I would say is same, because the main effect that was previously included would have already reduced the intercept variance. So that part's already been done. So that leaves 1 left. What happens to the slope variance? Got some votes for down? Lots of votes for down, yeah. This follows the rule, whichever variance term is in your equation, that's what it reduces. So this U1 is the idea that different clusters need different versions of this slope. The effect of x1 is stronger in some clusters than other. We're saying that maybe one of the reasons why it's stronger in some clusters than others is this level 2 predictor, explaining the random slope variance for this. Okay, how are we doing? Okay enough? Here, I need to like squish my page. let's do single spacing, make a little bit of room. Okay. Next up, another cross-level interaction. Now with the other level 1 predictor. Unyellow that. Where does this go? It goes right there. See, right here. Yeah, it goes, convenient for me, goes right here. What subscript does it get? 2, 1. Why 2? Because we're predicting beta 2. Why 1? Because 1 goes after 0. It's the first predictor of this slope. Okay, now the tricky part. What is it explaining? It's empty. It's empty. Where does it have to go? So residual variance, what happens to it? Got some votes for down? Zoomers? Couple nods? Yep, that's what it explains instead. This is the idea of a systematically varying effect. It's not that this slope is fixed. It's not that it's random. It's that it varies systematically as a function of this moderator and not otherwise. Whether or not this is okay to do is debatable. People fall on different sides of this argument. The problem is that if there should be a random slope in here and it's not here, the type 1 error for this cross-level interaction is way too high. Standard error is not big enough. It's underestimated. But if you test for the random slope and it's not there, and you have enough power to have found it, I think it's reasonable to try this as an alternative because it's an intermediary between fixed and random. But be prepared for reviewer 2 to yell at you about that. Question, can we directly put that interaction term in the level 2 intercept instead? We cannot, because this is a cross-level interaction, not a level 2 interaction. If it was between the cluster mean of x1 and the cluster mean of x2, then it would go into the beta equation after this term right here. But it's cross-level, which means it's predicting one of the level 1 slopes, and so it goes into the slope equation that corresponds to which variable's slope we're predicting. So the addition of this cross-level interaction, because there is no random slope variance that goes with it, means the residual variance is what gets reduced. And if the residual variance gets reduced, what happens to the intercept? It goes up as a compensatory fashion. What should happen to the random slope variance for the other level 1 predictor? Same. It's just hanging out, not changing. All right. Almost there. Unyellow that. Next question. What if we have another level 1 predictor, calling it x3, and I believe the instructions on this said it was going to be constant centered, right? We're not going to cluster mean center it. And we're going to put in a fixed effect for it. Where does it go? If I want to introduce a new level 1 predictor. Level 1? Yep, it's going to go right in here. Let me borrow one of those. And I'm going to call it beta 3 because 3 is after 2. And I'm going to say this is x3. What subscript does it get if it's a level 1 predictor? PC, yep. Every variable in level 1 should be a PC. Every variable in level 2 should only be a C. And it's constant centered, so we'll, let's say 8. Who cares? Doesn't matter. So if this variable is put in all by itself, actually, I'm not done yet, am I? What am I forgetting? How many betas do I have? 4. So that means I need one more level 2 equation. Right now I've only got 3. Yeah, level 2, x3 slope, and because I'm that kind, I have to space it over. I just like it when the equal signs line up. It makes me happy. It brings order to chaos. And gamma, I gotta spell it right for this to work. So you put a slash in front of it and then type out the Greek letter, and then you hit space and it becomes that. What's its subscript? 3? Did I hear that? 3 what? 3, 0. Yep. These all start at 0. Do I need to add anything else if I'm just adding a fixed effect? No. Okay. So if this variable is constant centered and I only include its fixed effect, what cardinal sin of multi-level modeling have I committed? This is a smushing problem, yes. So smushing means I am assuming that this new fixed slope is both the within cluster effect and the between cluster effect at the same time. In the story, I said that in reality, both of those slopes are significantly negative. So they're heading in the same direction. They might be of different magnitudes. So what happens to the residual variance if I add this new predictor? Let's make it yellow and make that yellow too. There we go. If I add a new level 1 predictor, what happens to my level 1 residual variance? Yeah, down. This one goes down. What happens to the intercept variance? Yeah, see this one, it depends on the size. It should go up because the residual went down, but if there's also a significant between effect that this is at least partially capturing, then I would think it's probably going to go down too. So it depends on the size, but I would say mostly down, down-ish for that. How about the slope variance for this predictor right here? Yeah, this one's the same. Nothing happened to it. If I were to fix this, how do I fix my cardinal sin of smushing? What would I have needed to add? And why does Iowa want me to restart my computer in the middle of my lecture? Stop it. All right, how do I fix this? Got 1 vote for CM, meaning cluster mean. Yeah, so if I wanted to fix it, unsmush this by adding the cluster mean, where does it go? Level 2 something. Yeah, the main effect would go in the intercept. Yep. So I need another one of these. Actually, that's right. I forgot I tricked it. I got to stay within the equation thing. Will it not let me? All right, we'll stick it over here. That's fine. And what subscript does it get? Oh something, because we're predicting beta 0. 03. And why? Because 3 comes after 2. That is correct. There we go. Nope, CM. X3 C minus, I don't know, 12. Who cares? Something like that. You can pick different centering constants at level 1 than at level 2. I think it makes your life easier if they match, though. So I typically try to pick the same one. All right, so if I were to add this, this was not included in the question. This is sort of a bonus question, if you will. Which variant should it explain? If I add a contextual effect via the cluster mean. Yep, random intercept, the one that's in its line. So I'll do CMX3 would make this go down again. So in total, whatever reduction you see in the random intercept is a function of the within effect plus the contextual effect. Need to make that yellow. Meaning it's the between effect that's doing the work, because within plus contextual is between. So the end total result in the reduction of random intercept variance is because of the between effect. Okay, do we have the strength for one more? Maybe? We can find it in week 10 of the semester. Persevere through this story problem from hell. But in a good way. So same story, now different pattern. So if I have a within effect that's negative and a between effect that's positive for a new predictor, the smushed effect that I would get is going to be some weighted blend of the two, and it's going to be closer to whatever the within is, because it's outweighted. So for that reason, I would say the residual variance is going to go down. The random intercept variance depends on just how different these coefficients are. Because if I don't have my contextual effect in here, there we go. The smushed effect says that both the within and the between slopes would be whatever negative number this works out to be in the middle, which is wrong. Like, it's not only saying there's no relationship, you're putting in the opposite direction of what it should be. So if you force a slope to be wrong, that will send the intercept variance up. That is a symptom, that is a sign of model misspecification. And I have seen that in life, and I have seen that in simulations work out that way. If you have a smushed effect that is completely wrong for the between effect, it will send your intercept variance up. But it should not affect the slope variance for the first predictor. So all in all, that's the story. And I looked through my answer key like 27 times, and I'm pretty sure that I got it right. But if you're finding that I didn't, please let me know, and I'll fix it. And you all get 2 points for playing. Okay. Does that help at all, or does it make it worse? Helps. Yeah, in these things, like, every predictor has a job to do. And so if you think, like, from a logical perspective, like, what kind of information is in this predictor, that logically dictates what kind of variance should be explained. And then there's some weird consequences. Anytime you explain residual, intercept has to go up at least a little bit. If you have a large enough cluster, you might not notice, though. Yes, please, go ahead.
When you said, so for the last one where we had the negative within and the positive between, you said that was, like, that's a sign of model misspecification, not the fact that the variances were down up same.
So the misspecification would come in if you fit the smushed effect, which says that both of these slopes should be the same for that variable within and between. But in reality, the between slope wants to be positive, whereas the within slope wants to be negative.
Okay.
Yeah, so then what you're saying is no between, you have to be negative too. And the random intercept is like, no, I don't like that, and it will go up. Yeah, I'm anthropomorphizing my variance components. But I know, you want happy models. It's like happy little trees and everything else. Okay. Questions otherwise, or things you want to hear again? All right, I will clean up the formatting on this and post it on the course webpage so you can save it for posterity. Make sure I save it so that I can do that. Otherwise, I've just lost, 45 minutes of work or something. That's no fun. Okay, I'm going to shut that down slowly. Shut down lecture 3 and open up lecture 5. So good news, folks. Number 1, this lecture only has 9 slides. That is a personal low for me, I think. I don't know that I've come up with a shorter lecture ever, so I'm kind of proud of that. But the good news otherwise is that we have covered everything in terms of like just new concepts. The rest of the semester is extensions. So that should feel comforting, right? We did it, exactly. Week 10, we got through like the meat and potatoes, as it were. There's a Midwestern expression for you. I actually hate potatoes, so maybe we got through the Arby's and French fries, or the cheeseburger and the curly fries. What I hate. Because they're not the same. The curly fries have enough other things in it that they don't taste like potatoes anymore. Yeah.
Do you like other French fries?
Certain French fries, yes. I like sweet potato fries and certain types of fries, but not like as a general rule. Like McDonald's fries are an abomination. Like I like that kind. So
That's
yeah.
your second strike. First you
I
said
know.
T-Swift's okay.
I
Now
know.
you said McDonald's fries are an abomination.
I know. I just like baked potatoes, like mashed potatoes, like that. Like
Baked potatoes are gross.
no, just no.
Unless they're smothered in sour cream and cheese.
Yeah. Yeah, if you need 18 condiments to make something taste good, like that's a sign right there that you're eating the wrong thing. That's so. Anywho, no meat and potatoes in this class. That's like saying fruit snacks taste like fruit. No, they don't. They taste like candy, and that's why my son will eat them. So we got all the sort of the essentials. Now we're on to just gravy. There's another expression, extensions, as it were. So what this little mini unit is about, you're not going to have a homework on it, but if you have data that look like this, I wanted to at least show you a little bit so that you can have some resources. What if you have different kinds of clustering in your data at the same time? That happens very commonly in longitudinal studies where you're following people in groups over time, like children who change schools or change classrooms. You might have patients that see more than one care provider, that kind of thing. So those sorts of situations are extensions of what we already have. It's just that things get more complicated because there's more than one source of clustering. So what we've talked about thus far, 2-level models in which one dimension of sampling is clearly nested in the other. So in longitudinal data, if we have repeated observations within persons or in cluster data, in this class, teachers nested within students or schools, something like that. Or no, students nested within teachers. Let me back that up. Maybe I need some French fries. If I can't get my levels right, it's not a good day. 3-level models, which I think is one of the topics that I have at the end, and we'll see if we have time to do any examples of that, but I gave you some readings if not. So we might have like clustered longitudinal data, for instance, if I have family research in which multiple occasions nested within multiple persons from the same family, within multiple families. In a lot of educational settings, if you have a lot of data, you might have students nested within teachers or classrooms nested within different schools. Some of you have schools within districts even. You could turn it into 4 levels. Districts within states. You can just keep going up and up and up. I think in Proc Mixed, it lets you have 8 random statements. So you could conceivably fit a 9-level model if you had to. Not sure how well that would go, but it's like theoretically possible. I don't know what the upper limit is on some of the other packages though. But in not every type of multi-level problem do you have strict nesting. Sometimes you have crossing instead. And the easiest way that I can explain this is that if you're not sure what's nested in what, it's a crossed model, not a nested model. If you could make an argument for it going either way, then it's a cross classification. So these models go by what some people would call synonyms and other people would call different versions of the model. So if you have, for instance, I have the next slide here, children that are nested within schools, and you also know what neighborhood they live in and not all kids who go to the same school live in the same neighborhood and vice versa, then what we have is a cross classification where students simultaneously have a cluster due to their school and a cluster due to their neighborhood, but neighborhoods and schools are crossed. Multiple membership models are analogous. This is where, like, you might say that if I have 4 years of high school and a student was in this school for the first year, so 25% of the time, and then they moved to another school, and they were in that school 25% of the time, and then maybe they moved again and they stayed in their last school for 2 years. So rather than give that child a random intercept that belongs to each school, you would weight it. So their contributions would be 0.25, 0.25, and then 0.5 for the school that they had 2 years worth. So it's like custom random intercepts that reflect the amount of clustering that they would be exposed to based on how they were sampled. I have a link to a free workshop that my hero Don Hedeker gave. I'm not exaggerating, he's like one of the smartest, coolest people on the planet. He was here last weekend with his band, the Polkaholics. It was an awesome show. If you ever get a chance to see him in the Chicago area, I highly recommend it. And he gave his Lifetime Achievement Award address the same day. So he's like a literal rock star and also a figurative rock star. He has some really great videos and slides, and they include code and data for these types of models. So if you're interested in learning more about each of these special cases, I direct you to that resource as well as others. Honestly, when you get to this point where you have a very specific kind of sampling design, I don't know that I could make up an example that would fit all of those cases. But these are some resources that give you examples of what it could look like based on your particular problem. So if I stick with the idea of kids, schools, and neighborhoods, kids are nested within schools and they're nested within neighborhoods simultaneously. So if I try to draw this graphically, if I have level 1 children nested in schools, if kids are also nested in neighborhoods, what that amounts to is a separate level 2 unit. So there's more than one level 2 intercept in these types of designs. But these are crossed, meaning that they stay orthogonal. The intercept for schools has nothing to do with the intercept for neighborhoods. So it's 3 different piles of variance, all uncorrelated at this point. And in terms of how we would go about quantifying and then explaining these sources of variance, it's the same principles. So if I had, say, a characteristic of the school, like whether it was a public school or a private school, that should explain school mean differences, the random intercept for this level 2 dimension. If I had some neighborhood characteristic like census data on socioeconomic status or something like that, that would explain why neighborhoods might have mean differences as a function of a neighborhood characteristic. It would explain this second random intercept variance. And if I have kid characteristics, that explains kid variance, residual variance in this case. So level 1 residual is differences between kids after controlling for what school they go to and what neighborhood they live in. But is this the end of the slide? If I have a kid predictor, right, and you have the answer in front of you, no. If I just put in a kid predictor, what have I done to it? Smushed it. Oh, how do I unsmush it?
You put in the cluster.
A contextual effect of some kind, right? But which one?
Both.
Both. So I would have school mean kid characteristic as a predictor of why schools have different outcomes, and I might have neighborhood mean kid characteristic as well. So there is a separate contextual effect for each distinct type of clustering with respect to your level 1 person predictors. So not a new concept, just more than one at the same time to keep track of. Beyond that, there's the potential for a random interaction term, which sounds crazy, but think of it this way. If you only have one unique observation per combination of level 2 unit, so in one of the examples that I gave you references to that I don't have time to present this semester, we have a problem of each subject responds to each item in an experimental design one time. So like they see a picture and they respond, or they read a word and do they decide if it's a word or a non-word, something like that. That's chapter 12 of my book, just specifically. If there's only one response per unique combination, then I can estimate a subject random intercept. So if I go with response time as an outcome, and let's say they're reading words or something like that, some people might be faster than other people across all the items. That's my subject random intercept. But some items might be easier than other items too. That's an item random intercept. So this is a common situation in, say, children measuring reading and reading fluency. You might be given a passage to read, and hopefully you're controlling different passages for their difficulty, number of words or reading level or that kinds of things. But to the extent that they're not exactly equal, then it matters what passage you give a child to read for their performance. So you can actually build in characteristics of the stimulus they're responding to and see to what extent those characteristics are responsible for mean differences. So some items might be responded to more accurately overall or faster overall. But if there's only one observation per combination of subject and item, then you can't have a separate variance component for the subject by item interaction. That is level 1 residual. It's like, why did this person take so long for that passage when I already know how fast they tend to be and how easy the passage tends to be? There's some unique, this person got tripped up by this passage despite their general tendencies, and we don't know why. That's level 1. Things that could explain level 1 residual variance then would be trial characteristics. Like, was this the first item that they saw? Maybe they're not very good at this task yet and they need some practice. Or was this the last item that they saw and they lost their will to live and they don't care? And so they're being slow for different reasons. So something about the unique combination of the subject and the item presentation could explain level 1 residual variance in this case. If, though, you have more than one, then you have the potential for an interaction term between the two cross dimensions that is separate from level 1 residual. So if I have multiple children who attend the same school and live in the same neighborhood, and I have that for most of the combinations in my data set, then I have the potential for a random intercept for schools at level 2. I have a potential for a random intercept at level 2 also for neighborhoods. And then I have yet another level 2 random intercept that pertains to the interaction of the two. Maybe kids who go to this particular school and live in this particular neighborhood have extra correlation to their data beyond what is expected just from going to this school and just from living in this neighborhood. There's something extra that happens with the crossing. And if that's the case, you can pull that apart as a third random effect. And then level 1 residual are the differences between kids that have the same combination. For those of you who are planning on taking G-theory next semester in the EMS program, that's what this is. But in that context, it's item differences, subject differences, maybe occasion differences, rater differences, and that kind of thing. But the idea that you're pulling apart all these different reasons for variability and your design affords you the opportunity to observe them separately, then you can estimate multiple kinds of random effects at the same time and explain each of them. So the example that I have actually is going to be of this kind, because why not? Yes?
What kind of variables at level 2 could help us to reduce that level 2 random interaction? The fixed interactions at level 2?
In that case, the only thing that I can think of as a realistic example would be a contextual effect of a level 1 person thing. Because you would have 3 potential contextual effects in this situation.
Yeah. Yes. Follow-up question. So we included one contextual effect at level 2, but let's say that contextual is related to the neighborhood, for example, for students. In those cases, could we try to select what pile of variance would we reduce with that contextual effect?
Yes. So
Wow,
there are, the way that I did this in the example, I was trying to be most straightforward, because honestly, this is something that I have to work out the math for to be more sure of what I think is happening. But yeah, like theoretically, you could decompose a predictor into 4 pieces, right? The kid part, the school part, the neighborhood part, and the interaction part. Because then the contextual effect for schools, for instance, would be the effect of the other kids who go to your school who don't live in your neighborhood. And Yeah, okay. Yeah, I got, this is a hand gesture sort of thing here. So if I have this situation, and let's say that I have a child predictor, there's 3 different kinds of contextual effects here. So if you have like your buddies, right, that all go to the same school and live in the same neighborhood, you have the mean of the kids who all share that commonality. That might have some impact on the scores of all the kids who are in that group, that clique, we'll say it that way. Then beyond that, the contextual effect of schools would be, what is the influence of the mean characteristic of the other kids who go to your school that don't live in your neighborhood? And then vice versa, what is the additional impact of the characteristics, of the mean characteristics of the kids who live in your neighborhood but don't go to your school? Like, you can pull apart 4 different things from one variable in theory. And that starts to break my brain a little bit. But if you think of this in sort of like an ANOVA kind of way, like you have a main effect of school, you have a main effect of neighborhood, you have a neighborhood by school interaction, and then you have a residual.
Yes. Now, related to this new term that we have in our model, we know that random components are hard to find sometimes or
Yes.
to estimate, so we can have convergence problems if we have multiple
Yes.
random effects. And we also know that sometimes we need more power for testing interactions in our
Yes.
model. So here we have both things at the same time.
Yes, you do.
How could we know, for example, if we have a model, we have our data, and some random variances were not significant, or maybe the interaction was not significant? How could we know that those results are because of the data we have and not the effects by themselves? For example, maybe those things would be significant with more sample size. How could we know that?
Well, so whether or not you need the random interaction, like a significance test for that is a likelihood ratio test, the same as usual.
Great.
The power to detect it is a function of how many unique observations you have for the crossing. So if you only have 2 kids who share the same school and neighborhood, that's going to make it harder than if you have 20.
Yeah.
And then we also can just literally carve up the variability into proportions, because these are 4 different uncorrelated things. So like, you can think of effect size as, well, this interaction is only 1% of the total variance. That's not very big. It would take a huge sample size to find it, versus this interaction turned out to be 5%, which is kind of big, but I don't have enough power to detect it. So I think the same general principles hold, but how many people you need, the answer is always going to be more. And if you run this model and you get dots back, that's your answer. Then it's what's known as over-parameterized, which is the fancy way of saying there's too much stuff in it. Make it simpler.
I feel like that word itself is
Over-parameterized. Yeah, that's one of those very long words, but you'll see that. Like negative, like downwardly biased means too small. Over-parameterized means too much stuff. Non-positive definite means broken. Like, you can just sort of shorthand these things, but when you write papers, you have to use the right words. Question, high-level correlation between both level 2, could it be a problem for the model? So by definition, these are not correlated. These are orthogonal sources of variance. Orthogonal, another one, not related. They're all separate. Now, where you would get correlations is if you started to estimate random slopes. And the random slope would only be correlated with the corresponding dimension of sampling's intercept. So if I wanted to know if the effect of, let's say, child characteristic X varied over schools, I could fit a random slope for child characteristic X over schools, and it would be correlated with the school random intercept, but not with any of the others. But technically speaking, this is still a 2-level model, even though it's insane. There's 4 different kinds of variance, 3 of them are at level 2. Yeah, I know. You're not doing a homework on this? So there's that. Yeah, random slopes. So let me blow your heads open for a few more minutes and then we'll call it a day. Does that sound good? So random slopes. You can have a level 1 predictor have random slopes over a level 2 unit, right? Cough, cough, homework question. I would call that the level 2 slope variance of the level 1 slope. Level 2 random variance of the level 1 slope, because it's the within slope that is varying across level 2 units specifically. But how many level 2 units do I have? Well, it depends, right? So they could vary. If I go back to a model that doesn't have the cross interaction, then I could have a kid characteristic vary over schools. I could have a kid characteristic vary over neighborhoods, both. And each random slope would only be correlated with the intercept that corresponds to that dimension of sampling. Here's the weirdness, though. I've never seen this in practice, but it is theoretically possible. Level 2 predictors can have a random slope over another level 2 cross dimension. Like, what? Yeah, they can. Some of you who work with like psycholinguistic data or experimental designs where you have people responding to the same type of item more than once under more than one condition, start to see things like this. I've never had to do this, but it is theoretically possible. So we want to prevent smushing of slopes, as we talked about. Contextual effects over each random dimension at level 2 potentially would need to be considered. And we can use cluster mean centering within every possible combination to make sure that we're at purely within with respect to that predictor. All right. Yes.
So in this case, we know that we will have two different entities, for example, schools and neighborhoods at level 2. Our level 1 predictor will be only one slope, or, well, one variable, or do we need two variables at level 1 to represent the level 1 from neighborhoods and the level 1 from schools? Or will be only one, and at level 2 we will have two?
The latter.
Okay.
Yeah, so if you have a child characteristic and you want to see if that predicts child outcomes at level 1, then you potentially have a contextual effect for that across schools, a separate contextual effect for that across neighborhoods.
Great.
Potentially a third across the combination of schools and neighborhoods if you have more than one child per combination.
Now, the interpretation of that level 1 predictor, we know that's the unique effect after controlling, but that after controlling for both slopes? at
After
level
controlling for both.
2? Okay, and at level 2 will be after controlling for level 1 only, or also for the other level 2?
If you have everything in the model, then everything is controlling for everything else.
Okay.
I'm going to punt on that question. There's another expression for you. Apparently it relates to football, where you decide you're not going to get a touchdown and you kick it instead. Is that accurate? Any football fans in the house? Does that sound right? Yeah. That's my understanding of what that expression means. All right. I don't want to do that. So does this sound insane or like something that we could do with just a little bit of a tweak of code? It's a, sounds like something you could eventually do? Hypothetically, maybe. Well, the good news is, unless this is your project topic, you don't have to try, and I don't think I let anyone try this. Most people came up with something that was too hard, and I said simplify. Just for your own good, right? It's not supposed to be a project, it's supposed to be a homework. And if you can get the core of it right, then you can add things, add things to the pieces here. Word is eventually going to start. I was going to foreshadow that it's actually not that bad. So there's a whole lot of data generation steps that I did to begin with, but let me just show you what it's going to look like, okay? So empty model. In this story, I've got children within primary schools and secondary schools. This is fake data from one of the Hawks multi-level books. I know for a fact it's fake data because there's exactly 1,000 students and exactly 50 primary schools. And they said exactly 30 secondary schools, but actually in the data set, 3 of them were miscoded, so it turns out to be 33. So this is your standard empty model just with a third subscript to keep track of the extra dimension. So you've seen something like this before, right? Like outcome, empty model, state of code, empty model, cool. Here's what a cross model would look like. Stata code adds another bar thing. This takes a minute to explain, but it's just a workaround because Stata doesn't have a way to do this directly, so it's like a hack. So you have a random school dimension for secondary schools, another random dimension for primary schools. And then you get 3 piles of variance back. In R, it's even more straightforward. Elmer, by the way, handled these beautifully. I was pleasantly surprised. It took just a split second. Here's just another random type. And even the insane, crazy crossed interaction thing, in Stata, I made a unique ID variable, threw that in there. I've got 3 now. In R, I did the same thing. So it's not that bad. It's not that bad. Where we're going to end up, though, is in terms of the amount of variance, it looks like the unique one does not contribute a whole lot. There is significant variance across each of the other dimensions, and so that's what we'll stick with. It's just a cross model. But see, this is just an extension. If you understand the idea of giving a clustering dimension a random intercept and potentially random slopes for your level 1 predictors, you understand the idea of like each characteristics of each type of sampling explain differences of that type of sampling. School things predict school random intercept. Neighborhood things predict neighborhood random intercept. Kid things predict residual variance. That all holds. Same principles. So, not that bad is the answer. Another reason why I know, by the way, that these data are simulated is because he has a predictor called child SES that ranges from 1 to 6, you know, because that's how you measure SES, and it has absolutely no variance at level 2, meaning he simulated it to be a pure within effect. So, except he only simulated it to be pure within for these 2 and not the crossing. There is actually a tiny bit of signal there. Good times. And yes, this happy error message. My level of okay is 0. It does not like a variance that has like 16 zeros before you get to a number. Those are essentially 0. All right, so this is what we'll do next time. I expect this may take the whole time next time. So once again, I'm prepped for Thursday. Yeah! That means I can finish the other things that are on fire and put this off for a few more days. All right, so not so bad, just extension time. There, something happier to look at. Any questions before we call it a day? Zoomers, we good? All right, then thanks for being here. Enjoy your 4 extra minutes of freedom. Let me know if you need anything. See you Thursday. Bye, Zoomers.